in two dimensions, this graph is in two dimensions, suppose. Okay, this is the graph corresponding with the function y equal f of x. But I perform the Riemann sum in one specific interval. Okay, by the way, the interval is one dimension because it's a segment, one dimension. Now you make a partition. This is the idea of the Riemann sum. In this case, called delta x, because the partition is on the x-axis. You can make partition, not necessarily the same width, but okay, normally to simplify the thing, you create constant width divided by m, and n represents the number of partitions. So I have a partition of 100 pieces, well, n is 100, and you take, and in any position, this is the beauty of this, in any position, you take intermediate value, any position I call x after I, because it's in the partition number 20, 21, and so you evaluate here in x I after. The beauty is that it doesn't matter. So you take, for example, the left endpoint or the right endpoint or the midpoint or any point inside the partition, and you evaluate and you compute the Riemann sum, the answer is the same. The answer is converged to the same value. Okay, this is the beauty to discover Riemann. Now, if you multiplication this value of the function, multiplication by delta x, why not give me this area? Okay, and the summation, every area from 1 to m is the Riemann sum, and so you apply the limit when the n approaches to infinity, que es sinónimo to say que delta x is 0. It doesn't matter. Some book put in this way, some book put in this way. Magically, this convert to the, well, magical, no, this is definition, integral from a to b of the function dx. Entonces now we study two semesters working in this special way, calculus 1 and 2. And we determine the antiderivative, so the integral, so indefinite integral. We study the collection of the function, sine, cosine, tangent, logarithm, exponential, power, and you determine the antiderivative. Okay, plus c, but I don't care c because I want to find the define integral. Okay, entonces you evaluate fa, fb minus fa. Entonces the beauty of this is that doing in this way is too hard. It's too hard because you need to know the summation of the specific function, and some summation is easy, but other no, is completely. However, the mathematicians develop the calculus, and in this case, relatively easy. Relative, no, it's not super easy, but it's relatively easy. Compute the antiderivative, evaluate, and you get the Riemann sum. In this case, according to this sketch, represent the area, but not necessarily area, because depending on the nature of the function, maybe it's volume, or maybe it's surface area, or maybe it's r length, you know, according to the, you know, so the magic of the integral calculus is one, one good approximation, not exactly, when you integrate magically, whoo, give me exact answer of the thing I try to find. Area, volume, surface area, our length, etc. Okay, this is the situation in Cal 1. I suppose you remember very well. Yes or no? Yes or no? A little bit? Guys, I need participation today. Now, let's move on to the graph in 3D. Okay, we are familiar, no? Because we practice to test with doing this. And we have, why not, a surface. Let me try to do my best. Suppose surface. Wow, not good. Okay, surface. Surface. Wow. Let me change the surface. Something like that. Surface. More general, no? And now we are doing partition also to find the Riemann zone. But the partition is not in 1D, it's in 2D. So one possibility is do rectangle on the XY plane. Pero no necessarily always in the XY plane, in any plane, okay? Entonces this point is, suppose, is AB, similar to we are doing this, and this is another value, okay, I'm going to call CD. So our region, guys, region, okay, put in green color, is 2D, is 2D. And we can represent like that, is the Cartesian product between this interval cross C, D. And well, this region I can do partition in that direction, in this direction. And we have, of course, delta x exactly the same. It's b minus a divided by m, similar to the one direction, this partition here. But we have delta y, is d minus c divided by m, because not necessarily it's the same number of partitions in the one axis. Okay, this is the beauty. Now, if you, for example, take one arbitrary rectangle here and you evaluate into the function, you get the function. By the way, this function, I forgot to say, is c equal f of x comma y, no? And you take arbitrary x and y, and you evaluate in this point, and you get f and xi after, comma yi after. This after, guys, don't frustrate with this after. This after is arbitrary crazy value, no? Inside the rectangle. Now, if you are doing the Riemann zone, well, the Riemann zone is the same idea. Is you are doing, for example, the summation from I equal 1 to m. I using this m because I suppose okay, I'm moving in the x direction, so I'm doing the summation in this order, in x direction parallel to the x of the function que is f xi after, comma yi after, multiplication by delta x. This is similar to the Cal 1, no? But when I finish this row, I continue with another row. So we are doing another summation. The j equal 1 to m of delta y. So in this case, both delta x, delta y. But actually, we have two kinds of summation. Look, two levels of summation. I'm going to cover every piece of the region. This is the Riemann zone. Entonces yo apply the limit. You apply the limit. It's the magic of the integral calculus when the n approaches to infinity and m approaches to infinity. So you are doing the infinitesimal square or rectangular very, very small, and magically, it's obvious, using the same idea, become like a double integral. Why double integral? Because when you see this symbol, limit and summation, que riman son, is equal somehow integral. The integral of the function in any point, and here you put dx dy, you put dx dy, dx dy, dx dy, or dy dx, or much better for me is dA, is this the infinitesimal area of the region, dA. What is most convenient to write like that? Because in this case, do not indicate order, dA in general. After I want to explain in detail the order of the integration over the region R. Over the region R. Okay? Entonces, let me write in this way, it gets much better. Maybe you don't understand 100% this idea, but I promise in a few minutes you understand very well. Entonces, this is the same. This is hard and this is easy. Well, no easy, pero a little bit more easy. Okay? Entonces, bueno, no, professor, okay, I understand, pero no. It's not clear for me. See, I asked you, what is the interpretation? What is the interpretation? So, the question that fly in the air is, what is the interpretation of double integral? Well, maybe you say, well, professor, is the Riemann sum. Okay, and the answer is perfect. But in this specific example I try to explain, do you have some idea? What was the answer can give me the double integral? Can give me, for example, 200. What is that? No idea.
Is it the area?
It's the area. Okay, it's the area
of the surface.
Of the surface? No, because participate one more guy. Participate this high, Mister. Participate this high. Look, this high participate in the game. Okay. See, you manipulate only this quantity. Maybe I agree with you que es the area, pero you introduce one important element in the formula que es the high, and this high, of course, we have infinity high, no? Infinity high. Okay, no problem. Good question. Good answer. Let me try to present one GeoGebra script with the animation que illustrate very well. Entonces, I repeat again the question. What is the interpretation for the double integral? Okay, let me try to do my best. Wish too much window I opened today. Okay, there you go. Okay, I create one script. To explain this idea. Okay, let me share the screen for that part. There you go. Do you see GeoGebra? Yes or no?
Yes.
Look like complicated. But no, don't worry. Look. Well, first of all, this part red color is a surface. Let me rotate to see a surface. Rotate. However, in order to explain the idea, I not delete, pero put on enable. the surface. Y I focusing on the most important part, que es the region and the partition. Que in this case, the partition I select, que is the 4x4. So I did partition 4 and X. Remember, X is the red color and Y is the green color. Okay, cool. Here I navigate, so the Riemann zone navigate like that. Look, this is K0 and the summation K1, 2, 3. I finish one row. I switch into the next row. 4, 5, 6, and so on to complete 16, no? Because of 4x4. And you evaluate one by one in the surface. So at that point is the famous f of x after y after. So don't forget exists this surface. Okay, don't allow to see more clear. I put it a little bit transparent, but okay. Now the idea for the calculus is when you travel. Okay, no problem. I understand you travel. You evaluate the function and you summation any brown color prism. They look like box, no? Now, when you summate, you integrate everything. Boom! Look at that. And only one, right? And only one. And when you apply the limit, well, the thing that we are doing is to increasing the number of the prism. Look, you increase, and this is an approach, of course. Look, increasing the number of prism. Approach, of course, off. Let me replace the surface again. Do you see this is what is that? What is the interpretation there? So Riemann zone is
The volume.
exactly. It's exactly I want to hear. It's a volume of the surface. So okay, of the region over the so the surface over the region. Excellent. This is one important conclusion. Everyone follow me? Do you understand very well this idea or no?
Yes.
Okay, but I have more. This is just the beginning. I have more information, more idea, more. Okay, cool. Let me close this because GeoGebra, I don't know why it's frozen. See, I don't save. Cool. Okay, close. Come back to the whiteboard. So you understand a little bit que the first interpretation. Remember, it's similar idea of the Cal1, no? Que the Cal1 you say, wow, the integral is the area. No, actually it's no area because I can modification the integrand function. Integrand, I suppose que es T. Integrand function. See, normally I take the original f of x, it's so big as volume. Okay? It's so big as volume. I promise after, no, today, I modify a little bit this integrand function. I put another thing, no, the elementary f of x, and give me another interpretation, no? But it's okay so far. Riemann zone, in the classical example, you take the original function, you get the volume. Okay, the volume, that volume. Yeah, look at that. That volume. Okay. However, frequently you assume que f of x, 1 is equal 1. So another example is 1. Entonces, si you assume que the function is 1, entonces we have double integral in the region R of 1 times dA. Que by the way is double integral in the region A of dA. Now, what is the interpretation? What is the interpretation of this? Uy, I suppose that the interpretation of this is the area, no? Yes or no? Makes sense? Makes sense, guy? Makes sense or no? Okay, makes sense. Entonces, definitely I don't understand anything. Is it volume or is it area? The meaning of the double integral. Well, it's both. Because suppose to understand this, look, suppose you have a box. Suppose you have a box. And the volume for this box is the multiplication, length, width, and height. Suppose this is length, this is width, and this is height. This is the volume. This capacity, space inside this. However, I assume que height es 1. Well, entonces the formula is reduced length times W. Oh, but this formula I am familiar. It's the area. It's area. So you suppose que this height is 1. Bueno, entonces actually the conclusion is, bueno, double integral give me volume. But I apply one strategy in which you assume that the function is 1. Entonces you have the volume, que is equal to the area, because one dimension is 1. Do you understand the idea? Entonces we are so far. The classical interpretation of double integral is volume. Okay, pero sometimes I using one resource, que es assume que the integrand function es 1. Entonces help me to compute the area. Entonces, bueno, professor, pero no necessary this, because in Cal 1, we don't need double integral to compute area. Okay. Pero in this case, we practice, and this concept, guy, I promise, is repeated. When the integral function is 1, entonces now my integral is another meaning, right? Okay. Entonces let's go to the, bueno, let's go to the computation. Yeah, computation of the one example. So you follow me so far. I want to erase the board. I immediately go to the first example, in which I explain clear, or I try, example 1, the computation for the double integral. No? Que super is. Compute the volume. You compute the volume. Okay, the volume of the surface. Surface is z equal x squared times y. Okay, by the way, I have no idea what is that. It's no paraboloid, it's no, it's, you know, so we know the name of the typical quadratic surface, but they are infinity surface, I don't know. Above the xy plane. Inside, so now it's important specification of the region. The region formed by the point 0, 0, 1, 0, 0, 1, and 1, 1. Okay, immediately I do the sketch of the region. So I have my famous XY plane. And this is the point 0, 0. This is 1, 0. This is 1, 1. And this is 0, 1. So this rectangle is my region. This is my region. Region R. And the surface, well, the surface you don't see here. You see in 3 dimensions. You see, for example, the z-axis perpendicular to the whiteboard. The z-axis perpendicular to the whiteboard. And you imagination the surface. But no, it's not important. I don't know. The integral, you set out like that. Double integral in the region R. The integral function is x squared y. And you put here dA. Entonces, they are, okay, who is dA? Let me explain in detail that part. Pay attention, this is super important. Bueno, dA es dx, dy, or dy, dx. And this depends on the direction of the integration. Actually, dA is in the partition one infinitesimal rectangular, not necessarily square, and this segment is dx, and this segment is dy. So we can interpret the action of the integration. So when you are doing this symbol or this symbol, the action for the integration is stretch. You suppose like elastic. I suppose that this square is elastic, and when you integration, for example, this is moving in that direction, or in that direction, the direction that you prefer. No, you prefer, because I will study in detail what is most convenient doing in this or in this. Depending on the example, don't anticipate to this. But your idea is, suppose that you have here the infinitesimal square. Boom. And you make a decision, integration in the y direction. Entonces, in the y direction, I like the blue color, I don't know why. You are stretching this like this. But when you are doing one first integral, under the supposition that you integrate dy first, you convert our famous rectangle in one strip. Okay, perfect. I did this summation in calculus, in integral form. Now, after that, you perform the second integral, in this case would be dx. Entonces, what is the interpretation of this? When you have a strip, you open the door, you open the window, sorry, like that. Stretch the window, and you complete the region. Okay? Okay, it's very, very similar to the thing we are doing in Cal 1. In Cal 1, you suppose a strip, and you open the window. No, we are more general. We have no strip, no. We have a rectangular, dA, formed by dx dy, and you integration in the way you prefer, guys. I want to show you right now, in this example, integration in 3 different ways. 3 different ways. Okay, I want to explain it. Do you understand the idea? This is important. Look like elementary, but it's extremely important. Okay. Suppose that I integrate x squared y. I assume integrate first with respect dx. Why, professor? Well, because I want to. And when you integrate with respect the y first, this is my region, no? This elementary I do in this direction. And after integrate with respect dy. So I can, well, the limit is clear. It's from 0 to 1. Look, this is 0, this is 1. And y, when you open the window, is also from 0 to 1, no? So how we compute that? Well, we compute that under the supposition that you are doing this. So we have no parentheses, and however, you have hypothetical imaginary parentheses, and you focus it, in this integral. So I copy separately in my mind. I copy x squared y dx. Yeah, I forgot the rest. I forgot the y and another integral. And the integration is obvious with respect to the x. It's similar to happen in the partial derivative, que the other variable you consider a constant. And so you consider a constant, y go outside, and we focus in this elementary problem of the calc 1. Entonces, y is an antiderivative is x cubed divided by 3, evaluating between 0 and 1. Es obvio que es 1/3, right? Because 1/3, 0. Entonces, so far, the answer is y over 3. Y I did the first integral. When I finish the first integral, I am doing the second. And the second is integral from 0 to 1 of the y over 3 dy. Okay, easy. 1/3 is a constant, put outside, you compute the antiderivative is y2 divided by 2, evaluating between 0 and 1. Es obvio que es 1 over 6, yes or no? Yes or no? Yes. Cool. Little by little you understand double integral. Okay. Now, some students say, well, no. I don't like this. I want to integrate first in that direction and expand in this direction. Okay, I respect opinion. Let's do it in this direction. So instead of doing in this way, I want to copy again the original integral. But I change the order. I put the y first and the x secondly. So I focus it in this integral first. Yeah, I copy separately, of course. Integral from 0 to 1, x squared y dy. In this case, the consideration is that x is constant. So you put outside. And antiderivative is y squared over 2. Evaluate between 0 and 1. Of course, you evaluate y. This is obvious. It's obvious que es obvio que es x squared over 2, ¿no? Now I come back to the other integral, que es x squared over 2 and the x. Okay, this is easy. It's 1/2 x cubed divided by 3, ¿no? Evaluating between 0 and 1, and the answer is the same. And this is no coincidence. This is a fact. So always happens that the order of the integral is completely irrelevant. You take the most convenient order, right, to evaluate the integral. I want to explain how you select what is convenient. But I have more information. In this particular, and this is called, guys, iterator integral. Iterator. The book called iterator. Iterator is a word using the mathematician to explain in one algorithm we are doing step by step. So we have one integral inside another integral. Okay, you compare the first, and after you compare the second. Iterate, step by step. However, in this particular special example que I select for you, we can look. Let me copy again my original problem. Is double integral. Wait a second. Let me change a little bit this. Double integral from 0 to 1. From 0 to 1. The function is x squared y dA. Okay. Suppose another way. In this particular example is possible. Not always is possible. When the limit is a constant, in this case is constant, is 0, 1, and the integrand function is separable. What means separable? Similar to the idea that we use in polar, no? You separate x squared dx and y dy, no? 0 to 1, 0 to 1, and multiplication. Not always is possible doing this, but in this case, yes. The antiderivative, this is x cubed over 3, evaluating between 0 and 1. And this is y squared over 2, evaluating between 0 and 1. X over is 1/3, x over is 1/2, together is 1/6. Same answer. And this is always positive, repeat again, when the limit is constant and the integral function is separable. Sometimes no, it's not separable. So we can do iterative, step by step. Clear, 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 or no? Or really confusing? Ajá. Entonces, the question can fly in the air. Bueno, profesor, pero you say something weird, I don't understand very well. You see que the limit is no constant. Oh, entonces I want to explain this. When the limit is no constant, because the thing we explained so far is double integral in rectangular region. I want to explain now double integral in general region. General, que no necessarily rectangular. And the rectangular piece, okay, because in the rectangular the limits are constant. But suppose one elementary example is very, very similar to compute the volume again of the same function. This is example 2, no? So it's compute the volume again. The function is z equal x squared y, the same function, but the region change. The region change. The region change like that. The region no rectangular, it's triangular. This is the region now. This is the region now. Okay, so I need to, I know the professor explained me it's volume. The meaning of the double integral and the region R of the function, integrand function, the surface, dA. Okay, cool. Now I need to make decision. Remember, we have the small rectangular here. Okay, this, the dimension of this guy is dx, dy, and we can integrate, suppose in this direction or in this direction, so vertical or horizontal. Let's do vertical first. So I stretch this infinitesimal rectangular vertical, because this means that I make decision to integrate in this order. dy first, okay, and dx secondly. Okay, we can do it another way. Of course, we can do it another way. Then let me try. The equation of this line is obvious. X plus y equal 1. It's the equation for this line. Then, see, you make a decision to compute first this integral dy. This limit here is y value, from y something to y something. And y, I see in the region vary from 0, get the top, the bottom here, and the y of this line is 1 minus x equal y, 1 minus x. Now is 1 minus x. Okay, this is 0. So in this region, well, it's general region, it's not rectangular, the limit is no constant, it's a function of the another variable. When you finish the first integral, well, entonces you open the window. You open the window in that direction. Now this thickness strip is expanding to the right and to the left from 0 to 1. because the value for the x and the region is from 0 to 1. So this from 0 to 1. Okay. Okay, let me copy more clear. I copy the double integral, in this case double integral, the integral function. I make a decision to integrate with respect to y first. Okay, cool. Now, the limit in y is 0 to the 1 minus x. Not necessary to write the y. I put the y equal because I want to illustrate that this is a y value. No? Entonces now when you finish this first integral, you make a decision, integrate with respect to x, que es from 0 to 1. Cool? It's doing. Okay, I copy if you want. If you want, no mandatory. The first integral, separately. Yeah, I know very well that we integrate with respect to y. Therefore, the x is constant. I put outside the game. Because the antiderivative of this is y squared over 2, evaluating between 0 and 1. Okay, cool, right? And you evaluate. This is x squared multiplication 0, 0 and 1 minus x. Sorry, this is the limit because it's a variable. So es divided by 2, 1 minus x squared. Everyone follow me? Okay, now you expand a little bit. You expand. Let's do it quickly. It's algebra. Sheesh, too much algebra. 1 minus 2x plus x squared by 2. Now we continue. Is x squared minus 2x cubed plus x to the 4th power divided by 2. And this is the answer of the first integral. I go to the beginning to say it's integral from 0 to 1 of this. Okay, by the way, if you want, you put a 1/2 outside and you integration x squared minus 2x cubed plus x to the 4th power dx. Don't forget dx. We are doing the last part. Okay, now it's 1/2, and the integration, this is x cubed divided by 3 minus 2 times x to the 4th power divided by 4 plus x to the 5th power divided by 5, evaluate obviously in between 0 and 1. I'm plugging in, and 0 is 0. And 1, no, and 1 is 1/3. Actually, 1/3, 1/2, 1/3, minus, in this case, 2 over 4, que es 1/2, again, repetition, no? Plus 1/5. And we combine that fraction divided by 2, so I multiply the denominator by 1, is 1 over 60. It does. And so what means that number? Well, no, that number is the volume. It's the volume, the volume of this surface over that region. It's the triangle. By curiosity. We can do in another order. Yes, we can do in another. Well, so far you understand the thing or no? It's easy, right? Not complicated. It's easy or complicated? It's easy, eh? Suppose in this, hypothetically, in this same problem, suppose another student doing in different way. I want to set up only the integration of the our region in different order. I promise that the solution is the same, right? To say this is x is a y. This is the famous line x plus y equal 1. And the point is the same, 0, 0, 1, 0, 0, 1. But I make a decision, integration in this direction. So our famous infinitesimal rectangle, I stretch, shook, horizontal. So, okay, no problema. And after I standing vertical, pero no. So I make a decision. Okay, in this case, integrate first with respect to x, because the stretching is horizontal. So I need to manipulate the limited. And finally, finally, dy and the limit also, right? Entonces the challenge is to determine the limit, no? The limit is, the region is from, when you extend it here, it's from 0, because x is equal to 0, look at that, here, to the x of the line, as a function of y. So x of the line is equal to 1 minus y. It's 1 minus y. Okay, this is x. So you can consider that our region we can represent for this inequality, no? And y, when you extend it, you will open the window in that direction, vertical, over and downward. Y go from 0 to 1. And this is the limit of the y, 0 to 1. This is another setup of the our double integral. And by the way, the answer doesn't change. It's the same answer. Okay, I don't want to waste the time with the stupid algebra. Okay, it's the same. So what is the conclusion I want to say? When we work in generalized region, maybe double integral, and also in triple integral, we studied not today, of course. The idea is, look, let me show you. The idea, suppose triple integral, to generalize more the concept I want to explain. Triple integral. You have here integrand function. And suppose that you integrate with respect to z first. Then this value is c, c1, c2. After you make the decision, integration dy. Okay, this is integral associated with dy, and this is y1 and y2 in the region. No? And finally dx. I make a decision in this order. I can change. Actually, I did that. I will do future. Okay. The situation that I want to explain is this limit not necessarily is a constant, because not necessarily our region is rectangular or cubic in 3D or prism. So basically we have two functions here. H1 is depending of x and y. So depending of the variable is missing. So we integrate with respect to z, and our limit is possible, could be, no 100%, but depending of the another variable x and y. And we have H2 depending f2. Okay, and y having similar situation as g depending of x, is the only variable, little by little decreasing the number of variables of the limit. Well, there are a specific example in which the limit is constant, but in general it's like that. And finally, value AB. That is, in the limit of the first variable, it's possible to have two variables, and the second integral only one, in the last integral no variable, it's just number. This is tradition, always is the same. Okay, I have another example. Very, very interesting. Let's do it completely. I want to do by hand. I want to do using Wolfram alpha. Okay, because okay, listen, what is the reason I insist in Wolfram alpha? Because unfortunately in Cal 3 we have a problem. We set up the problem, but good. This is Cal 3 using the concept of the Cal 3. But we are stopped because you have heavy algebra. Okay, stop me to continue. So now, see, I am doing everything by hand, but the rule is clear. The rule is clear. In the review packet, when they are doing the review packet, you are doing step by step, including the stupid algebra. However, in the lecture, no. In the lecture, I skip that because I want to focus 100% in the Cal 3, not in the algebra. Hello. Okay? And to say, wow, you forgive me. Okay, I say one of the answers, this triple integral or double integral is something. Because I didn't work for an alpha or I did in my graphic calculator. Okay? Okay, one more example. Everyone follow me so far, guys? Okay, cool. Look. Suppose compute the double integral. This is example 3, no? Example 3 or example, yeah, example 3. Compute this double integral in the region R of the function is x, y squared. It's a little bit different. dy dA. Oh no, dA. And no specification direction, dA. And the region, of course, is given. The region, of course, is given. The region is a line y equal x and the parabola y equal x squared. I say in between. This is my region. Entonces, when you finish that, the interpretation is a volume of this surface, okay, in 3D over that region. This is the region. Okay? Entonces, now, this is a moment to make a decision. But the professor explained me that it doesn't matter the small infinitesimal si I integrate in this direction or integrate in this direction. And the majority of the example is totally irrelevant, the direction. They are specific enough. But the majority of the example is this. And the integrations are basically, I determine, well, you determine the intersection point. It's obvious, right? This point is 0, 0. And this point is 1, 1. Okay, but how do you know that? Well, okay, you put together. The equation is x squared equal x, quadratic equation. Solve this by factorization. Es obvio que x is 0 and x is 1. Now, si x is 1 and x is 0, entonces es 0, 0,0 and 1,1. Cool. Okay, now I make a decision integration in this direction first. So x, y squared, dy. So my direction of the integration is in this direction. Guys, this is personally. I prefer that direction, but not always is good. Okay? I illustrate something little by little, you understand this. Okay, it's much better integrate in opposite direction, but in this case, when it's completely optional, for me, is I don't know, I feel comfortable. Entonces now my region, si I express it like inequality, is not necessary to do this. When you have practice, not necessary to do this. The region is between, this is the region expressing inequality. Is from x squared to x, right? Because who is the top and who is the bottom? The bottom is the parabola, the top is the line. And x vary from 0 to 1. Okay, because this is the indicate When you open the window in that direction, well, you go from 0x to 1x. Entonces now es obvio que the first integral, the limit are x squared and x. Cool? This is y value, and this is dy. And when you finish this, you integrate with respect to x, and it's from 0. Bam! This is our integral, double integral. Let's doing the last time I want to do is that, because I want to explain doing by Wolfram alpha, and you save time. And when you are doing your homework, no, in the written test, no, the written test we are doing step by step. Okay. So now we focus it in this integral. You want copy separately? Some students say, no, I don't want copy separately. I integrate this. You consider that x is a constant because the integral is dy. You put the x outside, and you focus it in this integral, que es y cubed divided by 3. So basically is x y cubed divided by 3 evaluate at x squared and x. Okay, entonces es x cubed over 3 minus x 6, no? It's 6, right? Because it's 2 double exponent multiplication 3. Actually, my function is you multiply, of course, x to the 4 power divided by 3 minus x to the 7 power divided by 3. Okay, no problem. I understand this. Now I did that part. As always, is expecting, give me no number. Give me a function that depends on the x. And this is the moment to open the door, open the window. Integral from 0 to 1 of the 1/3 if you want, you put outside like a constant, and you have x to the 4 power minus x to the 7 power dx. Okay, entonces 1/3, and you apply antiderivative, que es x to the 5th power divided by 5 minus x to the 8th power divided by 8, no? And evaluate in between 0 and 1. 0 is 0. And 1 is easy. 1 is 1/3, 1/5, minus 1/8. Okay, you're subtracting, multiplication. The answer is 15, 24, 1/4. 1/4. Cool. Now this represents the volume of that surface. Over that region. It's the first interpretation, no, that we studied of the double integral. Okay. Entonces I want to show you, so you have no question, what is the idea that we are doing in Wolfram alpha to avoid this. This is no, I select, of course, elementary example to illustrate the idea, because this procedure you apply in elementary example, you are applying the complicated example. The only is the long algebra. Okay, and the long algebra, everyone make a mistake. I make a mistake. Okay, because I change one sign mentally. I don't know. I copy wrong. So I get the wrong answer. This is the mathematics. It's very, very exact, no? So you don't get the answer, so you are in trouble. Okay. Now let's do it in Wolfram alpha. Wolfram alpha. I open, I suppose, Wolfram alpha. Let me share the screen. Wolfram alpha. Do you see Wolfram alpha? Wolfram alpha, the thing we were working before, using natural language. You can switch in natural language in white color or math input in purple color. I prefer that way, no? I prefer that way because we have the symbol, no? In the mathematical integral. Entonces, in this case, you use a double integral, pero no, you using define integral 2 times. It's the same, no? Then you copy. Do you see what Wolfram alpha? Yes or no? I share the, okay, cool. It's the thing I want to. So the thing is super easy. You open this integral. You put the limit. I suppose get the outermost integral. You put 0. Let me see the keyboard. 0. 1. Okay, here maybe you copy when I don't know. I copy another integral, no? ¿Qué es this? 1. Okay, nice. I like that. So you copy now. The limit is x squared. X, no? The surface is x. Don't forget the time. Y power 2. And the order of integration was dy first and dx secondly. When you finish to type in D, you press that button. Just in case, Wolfram alpha, copy a nice, elegant way the integral to verification. Okay, type in well, and this is the answer in fraction. So exact answer and approximation answer. The majority of the scenarios, the exact answer is the preferred. For example, in my lab, they want exact answer, no approximation. No? You type in 0.025, not good for my lab. You type in 1/4. Okay, good or not good? The thing I want to discuss now is, okay, the thing I want to discuss now is, for example, I give you now, okay, I want to share again the whiteboard. The thing I want to discuss now is, I give you, okay, one integral que some student is doing previously. Okay, one student, not you, another students, have this double integral, que is from 0 to 49, and y/7 and radical y of the hypothetic function. It's not important. So you don't need to compute this. You only need to understand how these students set up the integral and you change the order. This is the typical idea. Changing the order of integration. Entonces, the question can fly in the air. One. Okay. But what is the reason they need to change the order? Well, I want to illustrate, guys, in some example. Doing in one order is impossible. Why is impossible? Because sometimes you found a function that have no antiderivative. This is classical. This is classical. In calculus 2, you see one function, some function, no, que the antiderivative is impossible. The derivative is nice. Differentiate is nice. So es any function you can differentiate, but no any function you can find antiderivative. There are functions that have no antiderivative. I want to show you now. But this is not the question. The problem is I need to understand how this student set up this integral. So I need to understand the regions. So now I saw que X, bueno, okay, you see que the student set up the first integral, the first stage using dx. So this value is X. So X vary in between y over 7 and square root y. Okay? And y vary from 0 to 49. This is clear to looking the integral. So this is dx first, the student integrate first dx, therefore this is x value, x2, x1. Entonces, to understand, I recommend que you take, for example, in this inequality que represent the region R, you take this equation, so you take this part, and you convert to equation. To see, you know, the boundary. No? Entonces, you square both sides. Uf, ese parábola. Ese clásica parábola, y I did the parábola. Okay, why not? I take the second part, is this. And you get y over 7 equal x. Like equation. You take like equation, not to see. This is y equal 7x. Oh, it's a line. It's a line. It's a line passing through the origin, and the slope is 7. Wow. I suppose que in one point touch. I suppose que I want to determine now. Entonces, the x vary in between the parabola and the line. So I suppose that this is my region. Suppose this is my region. But it's important for me to determine this point. Well, this point is obviously 0, 0. But this point, it's not good. It's not, I have no idea. But okay, I put together, for example, this equation, and this equation together is x squared equals 7x, x squared minus 7x equal to 0, factorization is 0 and 7. Okay, cool. This value is 7. Okay, this value, I have no idea. Yes, I have idea. 49. Because as you plug it in, 7 in either equation, 7 squared is 49, or 7 times 7 is 49. At that point, at the point 7, 49. Okay. And also, I recognize que the guy que set out this integral is doing in this direction. Because he or she integrate dx first. However, I need to change to this direction. And end the story. This is my job. But my job is set out a new integral. And this new integral of the hypothetical function, I have no idea. But you change the order of integration. And it's obvious que this limit is y. Entonces, I go to the y of the parabola, que es x squared, to the y of the line, que es 7x. And when you open the window, in that direction or in that direction, I go from 0 to 7. Bang! End the story. And this integral give me exactly the same answer of the original case given. Cool? 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 Cool. No problema, it's easy. It's easy. Ajá, entonces I bring two more examples, very, very important. Well, I don't know si three, but two important, extremely important, and which is mandatory, change the sign of the order. Not because the question says change the order, no. It's because it's impossible. Doing in the order gets given the problem, and you change the order of the integration, and everything flowing nice, super nice. Okay, let me try. This is example, I don't know, remember si it's number 4 or number 5, I don't care, I lost the count. Suppose this integral, double integral, from x to pi, from 0 to pi. And the integral function is sine y over y dy dx. Okay? Well, the first thing I need to investigate is what is the region? What is the hypothetical region que the student is supposed to set out this integral? Okay? Entonces, I saw que the first integral using the y, go, y, go, to the lower limit to the upper limit. Y go to the x and pi. And x go, to 0 to pi. 0 to pi. Not 2 pi, just pi. So when this information, I try to do my best in order to understand the region. And the region is, remember, my recommendation, take one piece and convert to equation. Y equal pi. Y equal pi is a horizontal line. Y equal pi. And you take now the second piece, que is x equal y. Oh, it's a line. It's a line passing through the origin. Like that. Y equal x. Okay, cool. Y I suppose que this point, not necessarily too much algebra to understand, que este point pi. This is pi, and this is pi. This point is pi, pi. And this point is 0, 0. Okay, but we have two triangles, no? Two triangles. To say no, I know clear what part is okay, no? Okay, the integration direction, this student assumed was vertical, right? Because they integrate dy from x, gets this line to this. So I suppose, guys, that the direction of the integration is this. Which is this. And it's obvious that our region is this. Yes or no? This is our region. And the direction of the integration, repeat again, was this. How do you know? Because the y first. Okay? Okay, nice. Ready to compute that. No, what is the problem? Okay, when I try to isolate this, I try to do this integral. No, sine y divided by y have no antiderivative. You put in Wolfram alpha, something. Wolfram alpha, of course, realize you have no antiderivative. Therefore, Wolfram alpha compute the approximate using numerical value. So the integral function you have no antiderivative. Any software, so 50K software, realize that antiderivative do not exist and compute using numerical method. Okay. Simpson, one other method. Entonces now, entonces definitely this order que the student set out the integral is not good. Do you understand this idea? However, if I change the order in that direction, maybe I have x succeed. Entonces I need to set out a new integral. The integral function doesn't change. The only thing that changes is the direction of the integration. Entonces in that case, I go x from 0, this is x0, to the x of the line, que es, the line is y equal x, entonces es y, ¿no? From 0 to y. Makes sense, right? And when I open the window, in that direction, it's obvious that dy go from 0 to 1. Now, this example I try to do by hand because I want to illustrate the idea. Okay, I copy this integral separately. But the problem is that I integrate with respect to the x, sorry. So everything depending on y constant I put outside the game. Y is 0 to 1. Okay, y is 0 to 1. Y is 0 to 1 because when you have this strip in red color, I finish the integration in the x direction, I need to open the window. And open the window is upward and downward, no? And the y value is 0. Look at that. No, es pi, sorry. Es pi. Es pi. Es obvio que es pi. Sorry. Es pi. Okay. Es pi. Es pi. Maybe you change the question. Professor, it's not 1, es pi. Okay, entonces let's focus in the innermost integral y ahí detecting que sin y divided by y is a constant and basically your integration from 0 to y dx. Antiderivative dx is x. Evaluating between 0 and y. It's obvious. It's obvious. Okay, y, no? Y minus 0 and y cancel. Wow, fantastic. It's unbelievable. And now my second integral is sin y dy from 0 to pi. Okay, this is a piece, okay, of calculus. Okay, antiderivative sine is minus cosine. Evaluating between 0 pi is minus cosine pi minus cosine 0. This is negative 1, this is positive 1, but we have 1 minus in the front. Together is minus 2 and 1 negative outside, the answer is 2. Boom. Cool? Cool? One more, and that's it. Double integral. Double integral. I promise we are doing 1,000 double integral throughout the course. Okay, one more example. Double integral 0 to 1 and 3y and 3. And the integral function is e to the x squared dx dy. Okay, compute that. Okay, let's do it. Well, first of all, try to understand the region. I see that the student can set up this integral. The limit is this. So this is x bar. X bar vary from 3y to 3. And you y vary from 0 to 1. With this information, I try to do the sketch of the region. No? And this part is x equal 3. I convert to equation to understand the boundary. No? Entonces 1, 2, 3. 1, 2, 3. It's a line. 1, 2, 3. It's a vertical line. This line is the line x equal 3. And that part is 3y equal x. To understand much better for me, at least, you solve for y is x over 3. It's a line, of course, but it's log 1/3. Okay, therefore, I know wrong arise, no? Is like that. This is 1, approximately like that. Okay, this is 3, this is 1, this is the line y equal x over 3. Okay, entonces the student is doing this integration doing in that direction. So go from the line is this to the constant get 3. Because integrate first, but I need to change. Well, no, I don't know si I need to change to this direction. Okay, the y direction. The problem is when I try to do my best, I set up the integral. This function e to the x squared have no antiderivative. E to the x, yes, pero e to the x squared, no. No antiderivative. Mandatory, I need to change the order. I change the order in this order. E to the x squared, dy first, and dx second. Okay, entonces now so you integrate with respect to y. Okay, this is in the blue direction, no? I go from 0 to the y of the line. Okay, by the way, I isolate here against x over 3. And when you open the window, in that direction, I go in x from 0 to 3. Boom. So this double integral is equivalent 100% with this. Have the same value. However, this new one is easier to compute. Why? Because when I copy that, I consider that this is a constant. I put outside the game. The antiderivative y, dy is y, all in between this and this is x over 3. Okay. Now, finally, I copy the second integral, que es 0 to 3, of this function, que es x e to the x squared over 3 dx. And this is super easy by substitution. 1/6 integral from 0 to 9 e to the u du. E to the u is the nice function that the antiderivative is the same. It's 1/6 e to the u evaluating between 0 and 9. So 1/6 parentheses e to the 9 minus e to the 0. E to the 0 1, 1/6 parentheses e to the 9 minus 1. End the story. We finish. Cool. Okay. Well, let's do it quickly one more. And that's it, I suppose. Everyone follow me, guys? See, I recap the thing we covered today. We covered today the definition for the double integral. Do you understand very well the interpretation? What is that? So far, volume. So far. Or area. If the integral function is 1. And the iterate integral is dependent the order when you set out the integral. And we learn how you change the order, right? Okay, one more example. Easy, 0 to 4. And another integral 0 to 8 minus 2x of the hypothetic function dy dx. So when you see that, default is given the order of the integration. So this is a y value. So y vary from 0 to a minus 2x, and x vary from 0 to 4. Immediately, I try to do the sketch of the region. Okay, this is the region you take this equation. Okay, it's y equal a minus 2x. Oh, it's easy. It's a line. It's low negative. Y is 8. This is a 0,8. It's low negative 2. It's going down. And this point obviously is 4, 0. I suppose I don't need to explain that, right? And this is my region. And this is my region. Yeah, this is my region. Yeah, this is my region. Yellow. And the students or the guy can set out this integral doing in this direction. But I want to change in this direction. Okay. Let's see, I want to change in this direction. Well, I copy, double integral, bam, bam. The function doesn't change. The order of the integration change. And dx first, dy second. Entonces, the x go from 0 to the x value of this line. Okay, the x value of this line is, well, I have no idea. You take this equation and solve for x. Entonces es, you know, a ver, let me see, 2x is equal a minus y divided by 2. X is equal a over y divided by 2. You can leave it like that, or you separate, split the common denominator. Either way. Yeah, in my paper I split. It's 4 minus y over 2. 4 minus y over 2. Now, remember, we are doing in the right direction. In the right direction, you extending, open the window in that direction. Entonces, go from 0 to 8. End story. Cool? How do you feel in this double integral? Strong? Strong. This is just the beginning. I promise in next class I complicate a lot of this. Okay? We see transformation because we change the variable, but so far it's okay. This is the most important basic idea. Okay, stop sharing. Okay, guys, you continue. You have too much work. Continue doing homework. Que es extra credit. Continue the test number 2. Remember, this everything is due next Monday. Next Monday, to have the entire day. Have a good day. Okay, bye.